Hi everyone, welcome to Unprocessed Math. In this lecture, I'm going to talk about Riemann sounds. So, suppose we'd like to find the area under the graph of the function y equals x squared between the points 0 and 1. So that's going to be the area here. So that's the area under the graph of y equals x squared. That's the pink curve, and so this is the area that lies between the pink curve and the x-axis. So it's here. So obviously we don't have any simple formula for computing the area. So what I'm going to do is I'm going to use the areas of rectangles to approximate that area. So what I'm going to do is I'm just going to divide this integral 0 to 1 into 5 equal subintervals. So the distance between 0 and 1 is 1. And if you divide it into 5, that's going to be, so you see 1 minus 0 is the length of this subinterval. And then if you divide it by 5, then 0.2 is going to be the length of these subintervals. So we divide the interval 0 to 1 into 5 equal subintervals, and length of each of those subintervals is 0.2. Now I construct these rectangles, and for the height of rectangle, I'm going to use the value of the function in the right-hand side of these intervals. So for the first subinterval, the right-hand side is 0.2, and so I choose the height to be the value of the function at that point. And you see that I have a small rectangle here, and that's what I'm going to use for my approximation. And again, for the next subinterval, so I'm going to use the height of the rectangle to be the value of the function in the right-hand side. So it's going to be this. And similarly, say for this subinterval, the height of the rectangle is the value of the function in the right-hand side of the interval, which is 0.6. And similarly, you do it all the way to the last subinterval, where so you see, for the height of the rectangle, I'm going to use the value of the function in the right-hand side, which is this. So this distance is the value of the function y equals x squared at point 1, which is the right-hand side of that subinterval. And now I construct this green triangle. And you see that if you add up the areas of all these green, so I get 5 green triangles here, rectangles. So you have 5 rectangles here. And if you add up the areas of those 5 rectangles, so you see that looking at this picture, it's going to be larger than the area under the graph of this function. So you see that these green rectangles kind of overestimate the area under the graph of this function. So if I add up the areas of all those 5 rectangles, I will get an estimate, and it will be an overestimate. So let's try to find the areas. So now what we are doing is very elementary. So we are back in elementary school and trying to find the area of this rectangle, right? So this side is 0.2, and the height, so the height of that rectangle, or this side of the rectangle, is the value of the function at that point, and that's what I have here. So you see, so what you see here is the area of the green rectangle that you see there. One side is 0.2, the other side is the value of the function f in the right-hand side of that interval. And now you repeat this for the other 4 rectangles that you have there. Now for the next rectangle, again, this side is 0.2, and this side is the value of the function in the right-hand side, which is 0.4. Now, if you multiply 0.2, the length of this side, by the value of the function at the right-hand side, which is 0.4, which is f evaluated as 0.4, then that's going to give you the area of this second rectangle. So what you see here is the area of that green rectangle there. One side is 0.2, the other side is the value of the function at 0.4. And you just repeat this for the other three rectangles there. So, so let's look at, say, this one, right? So that's going to be the fourth rectangle. So this side again is 0.2, and the height of that rectangle is the value of the function at this point. So that's what you see here. So the area of this rectangle, the fourth rectangle, is given by this formula. One side is 0.4, one side is 0.2. The height of the rectangle is the value of the function in the right-hand side of that interval, which is 0.8. So if you multiply 0.2 by the value of f at 0.8, you're basically multiplying this side by that side, and the area of that rectangle will be given by this. So what I have here, so you see that I have 1, 2, 3, 4, 5, and all of them are area formulas for each of these rectangles. So I have 5 rectangles here, 1, 2, 3, 4, and 5, and you have 5 area formulas for rectangles here. So if you add them up, it's going to be equal to the sum of the areas of all these green rectangles, and that's going to be an overestimate for the area under the graph of y equals x squared. So now, so you notice that in this case, in this example that I'm showing you, I'm using the value of the function in the right-hand side of these intervals. So you see that, for example, for this fourth rectangle, the height of the rectangle is equal to the value of the function in the right-hand side of the that interval. So that's what I want. And this is called generally the right-hand rule, because I'm using the value of the function in the right-hand side as the height of these rectangles. So the formula that we have for the function f is just x squared, right? So f of x is x squared. So f of 0.2 is going to be 0.2 squared. So basically what I'm doing here is that I'm factoring out 0.2 from all these terms. I put it outside here, and then the value of the function f at 0.2 is 0.2 squared. The value of the function at 0.4 is 0.4 squared, and so on. The value of the function at 0.8 is 0.8 squared. So you just put those values, factor out 0.2, and if you use a calculator to compute this, it's going to be equal to 0.44. So this number is the sum of the areas of these 5 rectangles, and it's an OR estimate. So we know that now we had a rough idea that how large the area under the graph of this function is. So it's going to be some number smaller than 0.44. But now let's do this in a slightly different way. This time I'm going to repeat exactly the same process. I'm going to divide the interval 0, 1 into 5 equal subintervals. Length of each of those subintervals will be 0.2. But this time, I'm going to use the value of the function in the left-hand side of those intervals as the height of those rectangles. For example, if you look at this last interval, so you see the height of this green rectangle is equal to the value of the function in the left-hand side of the interval. And for example, similarly, if you pay attention to the third rectangle that you see here, is the height of this rectangle is equal to the value of the function in the left-hand side of that rectangle. And you just, and again, you use the area formula for a rectangle to find the areas of these 5 rectangles, add them up, and this time, so you see that if you add up the areas of these green rectangles, it's going to be an underestimate because clearly the sum of the areas of these rectangles are going to be smaller than the area under the graph of this function. And you notice that for the first one, so you see the first rectangle that you kind of have here, you want to use the value of the function on the left-hand side. So that the value of the function in the left-hand side, which is 0, is 0, right? You have y equals x squared, so the value of the function is 0. So here you basically had a rectangle with where this side is 0.2 and the height is 0. So f of 0 is going to be 0. So the first rectangle that you're using will have area 0. And now what you do is just almost exactly very similar to what we did in the previous example. So I'm going to add up the areas of all these 5 rectangles. So this is 0.2. That's the length of this side multiplied by the value of the function on the left-hand side. For the second rectangle, so it's this side, which is again 0.2, multiplied by the value of the function in the left-hand side, which is f cat 0.2. This, and then the third rectangle, this side is 0.2. The height is the value of the function, give the left-hand side at that into. So it's going to be 0.2, which is this side, multiplied by the value of the function in the left-hand side. And you just repeat this for the other 2 rectangles. So you see, if you add up, so you have kind of 5 rectangles here. One of them that has area 0, which is fine. And now if you add up the areas of all these rectangles, you're going to get an estimate that will underestimate the area under the graph of the function, but we will have an estimate. So again, similar to the previous example, factor out 0.2 from all these terms, put it outside, and then the value of the function at 0, your function is x squared, so it's going to be 0 squared. Value of the function at the value of the function at 0.2, use 0.2 squared. Value of the function at 0.4 is 0.4 squared. Value of the function at 0.6 is 0.6 squared, and so on. So if you use a calculator, you compute this number, it's going to be 0.24. So this is going to be an underestimation. So this is basically an underestimate. Now that the area that we are looking for is going to be larger than 0.24, but smaller than 0.44. So now we don't know what the area is, but we have a rough idea. It's going to be some number smaller than 0.44 and larger than 0.24. Now, let's do something slightly different. So you see, in the previous example that I showed you, so in the first example, we used the values of the function in the right-hand side. In the second function, we use the values of the function in the left-hand side for the height of these rectangles. We can also use the values of the function at the midpoint for each of these intervals as the value of the as the height of these rectangles. So you see, for example, in this last rectangle that I have here, so what's the area of that rectangle? So this side is 0.2. I'm again dividing the interval of 0.0 and 1. So basically we are dividing this interval into 5 equal subintervals. But you see, the height of this rectangle is this value of the function at the midpoint. So this side is going to be 0.2, and the height is going to be the value of the function at the midpoint. So the midpoint of 1 and 0.8 is going to be 0.9. So actually the midpoint is 0.9. So the value of the function at 0.9 is going to be the height of this rectangle. Then when you multiply it by this side, so this is that I give you the area of that whole rectangle. Just repeat the same formula for the other 5 rectangles we have here. So let's look at this third rectangle. this side is going to be 0.2, and the height is the value of the function at the midpoint of 0.4 and 0.6, which is going to be 0.5. The midpoint is 0.5. So the area of this, third rectangle that you see here will be given by this formula, because one side is 0.2. The other side is the value of the function f at the midpoint, which is 0.5. So you apply this for all these 5 rectangles that you have. You use the value of the function at the midpoint for the height of those rectangles, and then you add up the areas of all those rectangles. This time I'm using the midpoints, and this is called the midpoint rule. So you can use the left hand, you can use the values of the function on the left hand side of the intervals. Then that is you're using basically left hand rule or right hand rule or midpoint rule. So here I'm using the midpoint, so this is called the midpoint rule. And if you add up the areas of all these 5 rectangles that you had here, again, that's going to be an estimate for the area under the graph of this function. So you can easily compute this. So you factor of 0.2 from both these 5 terms. You put it here, and then f of 0.1 is 0.1 squared. F of 0.3 is 0.3 squared. And notice that 0.3 is the midpoint of the second interval, and so on. So if you add up all these numbers using calculator, it's going to be 0.33. And now in this case, if you're using midpoint rule, it's hard to say if this is an underestimate or overestimate, but it seems to be a better estimate than you're using the midpoint rule. So again, this gives us a rough idea that what the area under the graph of this function might be. So it's going to be a number close to 0.33. So you see, given a function f, you can, and an interval 0, 1, or in general it could be a and b, you can divide it into, so here what we did is that we divided into 5 equal subintervals, and then for each of those subintervals you can, for the height of these rectangles that you want to use for your approximation, you can use the left-hand rule, right-hand rule, or midpoint rule, and each of them will give you an estimate. And this is how you can use basically the area formula for rectangle to approximate the area on the graph of functions. And this is the main idea behind Riemann science. So we are using the area formula for rectangle to approximate the area under the graph of some function. And it wouldn't matter really if you had the function y equals x squared or anything else. If I had x cubed or any other function, all you need to do is that, when you're evaluating the value of the function that's 0.1, so because the function is x squared, it becomes 0.1 squared. If you have some other function, then going from here to here, you had another formula, so you use the same formula, and that gives you an approximation. So if you fully understand the left-hand rule, right-hand rule, and the midpoint rule for this simple example, y equals x squared, if you're given any other function, the only change is that when you're going from this step to that step, you have just a different formula, but it's not going to change anything much. Okay, so now let's look at, so you see in all these, the 3 examples that I showed you, we are dividing the interval 0, 1 into 5 equal subintervals. But what 5? But why 5? Why not 6? Why not 7? Because you see that if you use more intervals, your approximations will be more and more accurate. And in general, if you so let's try to do this in a more general setting. So I'm going to assume that I have an interval A and B. So instead of 0 and 1, we have A and B. And instead of dividing it into 5 equal subintervals, I'm going to divide it into n equal subintervals. So then what would be the length of each of these subintervals that you're going to get there? So if you subtract A from B, so B minus A is going to be the length of this interval. And they're dividing it into n equal subintervals. So the length of each of these subintervals is just going to be simply B minus D divided by n. So, and that's generally called delta x. So delta x is the length of this interval, which is B minus A, divided by the number of intervals you want to have. So now the length of each of these subintervals are going to be delta x. That actually, in the previous example that I showed you, the delta x was, so maybe I'll just write it down. So delta x in this case was actually 0.2. So, and you see that it repeats in all these area formulas because that becomes the one side of all these rectangles that we are going to create. Okay, and notice that after you have these subintervals, so then you had these subintervals and you have the endpoints, right? You start from 0, the next endpoint is 0.2, the next one is 0.4, 0.6, 0.8, and 1. And if you want to do that in a more general setting, so you can see that so you will have a sequence of endpoints. X0 is going to be the starting point. X1 is going to be the next point that you get in the sequence. And X2 becomes the third point, X3 becomes the fourth point, and so on. So if you divide the interval AB into n equal subintervals, then the length of each of those subintervals will be delta x, and the n points, I'm going to call them x0, x1, x2, x3, all the way to x. And the formula that you will have for xi's, the i's general, you can substitute I by 0, 1, 2, and so on, and get the value of xi. So it's basically the xi is going to be the starting point plus a minus 1 plus I minus 1 multiplied by delta x. So this is the formula that you have for xi's. Xi is going to be a plus I minus 1 times delta x. And you know that delta x is li minus a or 2. So in general, this is the formula you have for x past. So xi is equal to a, which is the left-hand side of that interval, plus I minus 1 multiplied by delta x, which is b minus d over n. And notice that your so here you're dividing this interlogging through n equal subintervals, and the ith interval is going to look like this. So the ith interval is going to look like xi minus 1 and xi. So you see that the first interval looks like x0 and x lot. So the right-hand side index matches the number of this subinterval. So this is subinterval number 1, and the right-hand side is x1. So you see the subinterval number I will look like xi and xi minus 1, meaning that the right-hand side of interval number I will be xi, the left-hand side will be xi minus 1. This will be important if you're deciding to use the left-hand rule, midpoint rule, or the right-hand rule, right? So the ith subinterval looks like this, and the right-hand point is xi, and the left-hand point is xi minus 1. And now, so if you divide the interval AB into n equal subintervals, if you use the right-hand rule, notice that your interval looks like xi and xi minus 1. So what you do is that you multiply delta x. Remember, the delta x is the base of those rectangles that are all equal. So you multiply delta x by the value of the function in the right-hand side, and this gives you the area of the ith rectangle that you're constructing. So you see, what you see here is the area formula for the ith rectangle. One side is delta x, the other side is the value of the function in the right-hand side of this interval. And if you add them up from I equals 1 to m, it means that you're constructing all these n rectangles, you're adding the areas of all those rectangles up, and this sum is going to give you an estimate for the area under the graph of the function f, and we call it S or n. R means that we're using the right-hand rule, and n means that we're using n sub n to us. But if you use the left-hand rule, then we should use the value of the function in the left-hand side of these intervals. So this becomes the formula for your approximation if you're using the left-hand rule. So what you see again here is the area of the ith rectangle that you're constructing there. Delta x is there, is the length of one side. Basically, it's the length of the base, and the height of the rectangle is the value of the function on the left-hand side. And this formula gives you the formula for the left-hand rule, if you're using the left-hand side points for the height of the rectangles. And for the midpoint, so you see for the midpoint, you're going to use the same, basically so you have all these rectangles. The base is going to be delta x, but for the height, you want to use the value of the function at the midpoint of this interval. So for the midpoint, you add xi by xi minus 1 and divide by 2. So you see that this is the midpoint of that interval. And so the value of the function at the midpoint, that becomes the height of the rectangle multiplied by delta x. That's the base of those rectangles. And what you see here, again, is the area formula for a rectangle. But you have n of those rectangles, you need to add them up. And if you add the areas of all those rectangles, the sum is going to give you an approximation for the area under the graph of the function f. And this basically, basically now it should be kind of roughly clear where this formulas come from, and that's what we do, what we use to approximate the areas on the graphs of general functions f. So and again, I want to emphasize that what you see here, put aside the sigma, and so when you have the sigma, so the sigma from 1 to n means that you're adding up the areas of all those n rectangles. So what matters is inside, and inside all you're seeing is the area formula for a rectangle. One side is delta x, the other side is the value of the function in the right-hand side. Here you have the value of the function on the left-hand side. Here you have the value of the function at the midpoint. And that's where these right-hand rule and left-hand rule and left-hand rule cells from. Let me show you an example. Now I'll let go back to the same example we were working with. So remember that in all these three examples that I showed you earlier, we are trying to find the area under the graph of this function y equals x squared. And if you have watched the previous lecture about definite intervals, so the area under the graph of the function x squared between 0 and 1 is actually denoted by this definite integral. So that's the definite integral from 0 to 1 of the function x squared. Now, so now we are trying to actually try to compute this area exactly without any errors. We don't want any overestimate, any underestimate, any estimate. We want to get something very accurate. So what I'm going to do is that we are going to take this interval between 0 and 1. So you have the interval between 0 and 1. So you have 0 and 1, and you divide it. So what you do is that it's basically the same graph. But this time, and the goal is to find this area. So what we do is that, so in this case, the interval a and b is simply 0 and 1. And we are going to divide it not into 5 equal subintervals. We are going to divide them into 10 equal subintervals. So that, and we are going to keep this in general. And because you know that the best possible n is the largest possible n. So you want to make this n as large as possible. But let's divide this interval into n equal subintervals and try to give an estimate. So if you do that, then this is going to be, so basically you're dividing this interval from 0 to 1 into n equal subintervals. So you're going to have similar to what we saw before. So it's going to be x0, x1, x2, and so on, right? So these are the endpoints of these intervals. And we had a formula for xi. So xi is just going to be a plus I minus 1 times delta x. That's what I showed you earlier. So that's as using this formula. So xi will be given by a plus I minus 1 times delta x. In this case, delta x is the length of this interval. That's 1 minus 0 divided by n. So in this case, delta x is going to be 1 over n, which is reasonable because we are dividing this interval of length 1 into n equal subintervals. So the length of each of those subintervals is going to be 1 over n. So I have delta x is equal to 1 over m. I have I minus 1, and in this case, a is the left-hand side of intervals, which is 0. So your xi's, you can just use xi, this formula, and if you just simplify this, that's going to be I minus 1 divided by n. So xi is equal to I minus 1 divided by m. Now I'm going to use the right-hand rule. Say, let's use the right-hand rule to compute our estimate. So this is the formula we have for the right-hand rule, but remember that we have a nice formula for xi. Xi is I minus 1 divided by n. Now, so delta x is 1 over m, and xi minus 1, as I just showed you, is I minus 1 over n. So if we use n equal subintervals to get an approximation using the right-hand rule, it's going to be given by the sum, and I know what xi is, I know what delta x is. You substitute here, and in this case, we know that what f is. So f is x squared, and f of I minus 1 over n is just simply going to be I minus 1 over n squared, because the function f just squares whatever you give to f, it's going to square it. F of x is x squared. F of I minus 1 over n is I minus 1 over n squared. Now let's just simplify this. I can write this as I minus 1 squared divided by n squared. That's the same thing, multiplied by 1 over m. And then you see that you have 1 over n squared multiplied by 1 over m. So n squared comes in, that's n cubed. I can put it outside, so that becomes 1 over n squared. And inside the sigma, you have these sigma I minus 1 squared. And so here we're using the sigma notation, and what this means is that the sigma notation means that substitute start from 1 all the way to n, substitute i's by 1, 2, 3 all the way to m, and add up these numbers. So if you substitute I by 1, you will get 0 here. If you substitute I by the max number by 2, 2 minus 1 will be 1. So you get 1 squared, and then similarly you will get 2 squared all the way. The last number that you're going to get will be when you replace I by the largest number here, which is m. So the last number that you're going to get will be n minus 1 squared. So the sigma I from 1 to m of I minus 1 squared is actually this, refers to this sum. So you want to add up the squares of natural numbers started from 0 all the way to n minus 1. And for that, we had a formula. So this is a formula that you can use. So if you add up the squares of natural numbers starting from 1 all the way to k, you have this nice formula. And so in this case, k is n minus 1. So I'm adding the squares of natural numbers. So this is just 0 squared. That's just 0. So I'm adding the squares of natural numbers starting from 1 all the way to n minus 1. So this sum can be computed using this formula. So all you need to do is just to replace k by n minus 1. And if you replace k by n minus 1 in this formula, this is what you're going to get. So what I have here is basically k times k plus 1 times 2k plus 1. And if you notice that this is the formula I had in the previous page, and all we had done is that we have replaced k by n minus 1. So now I have this nice formula for the sum. So let's just simplify this. So n minus 1 plus 1, that simplifies to n. The first term is n minus 1, and this is 2n minus 2 plus 1. That simplifies to 2n minus 1. So if you simplify, that's what you're going to get. And now, so here, ideally, that in order to get better and better approximations, we want to make m as large as possible. Basically, we want to use as many rectangles as possible, because when you use more rectangles, your approximations become more and more accurate. But you see that when n is large, then suppose n is a medium, right? This 1, you can ignore 1 against this 2 this is going to be about 2 million. So when n is large, you can actually ignore this minus 1 against n. You can also ignore this minus 1 against 2n. So this expression is going to be approximately equal to 1 over n cubed. And now all I do is that I ignore this minus 1 here. So I get, so you ignore these minus 1s there, and that's how you're getting this. And if you simplify this now, n's will cancel, so you have n, and n, that's n cubed, that cancels the n cubed. So you're giving 2 divided by 6, which is 1/3. So if n is large, this is approximately 1 over 3. But if you take the limit, then n goes to infinity. It means that, you take these, you start, doing this process, and you make n as large as possible. So the ideal n is infinity. And if you let n go to infinity, then the limit of this expression is going to be 1/3. And what does this mean? It means that if you divide the interval between 0 and 1 into a very large number of n subintervals, and construct all those rectangles and add up the areas of all those rectangles, then it's going to be equal to very close to 1 over 3. And in the limit, if you do this, if you divide it into infinite subintervals, actually you're going to get 1/3. So in the limit, you're going to get the area under the graph of the function x squared between 0 and 1. And this is accurate now. So if you let n go to infinity, if m is anything less than m infinity, then that's going to be an estimate. So if you use n equal to, you have these 1 million rectangles, that's going to give you a very good approximation, but it's not going to be accurate. But if you let n go to infinity, then in the limit, you're going to get 1/3, and 1/3 is accurate. But I'm going back to the first examples that I showed you. So you see that then you use the midpoint rule, we almost got 0.33. And now we know that the area under the graph of this function is precisely equal to 1/3. And this is roughly how the Riemann sums work. So you divide the area under the graph of some function into a finite number of subintervals, n, and if n is anything less than infinity, then you will have an estimate. But if you let n go to infinity, then you will recover precisely the area under the graph that function. And this basically gives you the idea of Riemann sums. And there's nothing particular about using the left-hand rule. You can use the right-hand rule and repeat the same process. That would be a good exercise, that you just repeat what I just did here using the right-hand rule or midpoint rule, and send outline these sigmas and see if you can get 1/3 as well. So it doesn't matter if you use the left-hand rule, right-hand rule, or midpoint rule. If you left angle to infinity, all of them will give you the same number, and that number is the area under the graph of the function. So this finishes our discussion about Riemann sums. For additional practice, you can take a look at the Apex Chapters 2 textbook. It's a free textbook you can download online. And this is section 5.3. If you need any additional help, check out matchmefusions.com. I'll put the links for both these resources in the description.